Section 4.11, the central limit theorem. The objectives of this video are to define the central limit theorem, to present the logic behind the central limit theorem, and to calculate probabilities using the central limit theorem. Well, why the central limit theorem is important is because under certain conditions you can approximate some distribution with normal distribution even though the distribution is not normally distributed. In that sense, it's very powerful for distributions that are skewed and even discrete distributions. Let S1 to be a sample with outcomes x1 to xn, and it's a sample from a random population with mean mu and variance sigma square. So the mean is defined by x1 plus x2 plus xn divided by n. Okay, and then let's consider that we take another sample of size n, and so S2 is composed for some other x1 to xn. So let me do a little drawing to illustrate what we are doing. So we have a distribution, whatever the distribution, and that distribution has a mean, mu, and standard deviation or variance sigma square. Now initially we have x1, so x1 is so we take n points from x1. Let's say we are taking, this is x1, so this corresponds to x1, and so from this sample we have a mean that is the sample of those elements, and then we take a different sample, and I'm going to do it now in green. So we have another sample, the same size, n elements. Now that sample is S2, and then we take a different sample. That sample, let's do it in red, so the same number of elements, and that sample is S3. So for each one of the samples we take the mean. In the first case that was the mean, in the second case we are going to call it x2 mean, and is the sum of x1 plus xn from that particular sample, the one in green, divided by n, and the same thing for x and the sample 3. Sample 3 is going to have another mean, so we have x1 plus xn divided by n, and those elements differ. So to illustrate, those elements are the ones in red, in the sample in red, and this will be the ones in blue. So if we take all the samples x1 and x2 and start to do our own distributions of samples, so in this case now we are going to have x mean, so we have the means, and if we collect them all, so we are going to have something like that looks something like that. So it actually will look like a normal distribution, but this is the distribution of the means of all the samples that we have. So the central theorem is telling us that x1, x2, and so forth are normally distributed. Now we have to take into account one fact, and is that in all the cases the size of the mean was the same, so n was the same. Okay, to illustrate the central limit theorem, let's have a look to this wonderful applet by David Lane at Rice University. If we follow the link provided in this page, we can go straight to the applet. In the top part we have a distribution. In the bottom on the right we select the type of distribution that we have originally, So we have a normal distribution, as we can observe. We can have a uniform distribution. We can have a skew distribution, or we can create our own distribution with the mouse. So if I move the mouse, I have this distribution. Anything that I can't sketch with the mouse, it will produce a distribution. On the left hand side, we can see the mean is 14 in this case, is the one in blue, and the median is 11. So any distribution is possible, so we can try with any distribution. In particular, I'm going to try with a skew distribution, something that is not a normal distribution. Now I'm going to make some sample, and this is an animated sample. 1, 2, 3, 4, 5. So we have 5 different elements, and from those elements, from this sample, this is the mean, the one in blue. So then if I do again 1, 2, 3, 4, 5, another sample, and this is the second mean that we have. So I'm going to press here 5, so it's going to take 5 more samples. So right now we have 2 samples. I'm going to have 5 more samples. So these are the samples, well, the means of the samples. So we have in total 7 samples. So this is the mean of the sample, 5.55. 5.55. This is, and the median is 6. Now, if we look to the original distribution, the mean is 8.08. So it differs. So what I'm going to continue doing, I'm going to take another 5 samples, and look, now the mean is 7.23. It's getting closer to the 8.08. And I'm going to continue with another 5, 7.29, another 5, 7.85. So it's getting closer and closer. So I'm going to take 10,000 samples. Okay, 10,000 samples. So we have that the mean is 8.11, very close to the mean of our distribution, which is skewed. And if I continue doing it, another 10,000, 8.06. It's very close. Now, the interesting thing is the distributions of the mean, you can see very symmetric, is normally distributed. So that's the idea of the theorem, that the distribution of the means is normally distributed. So you can access this applet and play with the concept. The central limit theorem says that if S1 is a random sample from a population with mean mu and variance sigma square, and x1 bar is the sample mean, then if n is sufficiently large, x is distributed as normal with parameters mu and sigma square over n. That means that if our sample is large enough, then the sample mean x bar is distributed normally, and we can use the normal distribution to compute probabilities. Now the question is, what is large enough? Well, according to the book and some empirical evidence, they suggest that a population of n bigger than 30 is large enough. Summarizing, the sample mean is the mean of the population, and the sample variance is the variance of the population divided by n, and is normally distributed. Let's consider the following example. This is example 4.17 from the book. What we have is that x denotes the number of flows in 1 inch length of copper wire, and the probability mass function x is presented in this table. So for this table we have a discrete random variable with values 0, 1, 2, and 3, and the corresponding probability 0.48, and if I plot the probability 0.48 in this plot, so we have 48 more or less in that region. For x equal to 1 we have 0.39, something over there. For x equal to 2, 0.12, so that will be something closer to that, and for 3 is 0.01. So we have probability mass function, so it's not even continuous, that is defined at 0, 1, 2, 3. So for this population we need to compute the mean and the variance. So how do we compute the mean and the variance? So remember that the mean of this population is given by the sum of xi multiplied by pi, where pi is the probability of x equal to xi, so the corresponding value from the table. So this, in a much more compact way, is the dot product of this vector multiplied by this vector. So I'm going to call this vector x and this vector p. So mu is equal to x vector dot product p vector. And the variance, so the variance sigma square is equal to the sum of xi minus mu square multiplied by the probability of x equal to xi. So this one also we can compute it in a vector form. So we can say that x is sigma square equal to vector x minus mu. Mu it's a constant, so we have to subtract to every element of x mu, and we square this value, and we do, and this is an element wise operation, so we square each one of the values, and then we do dot product with p, dot product with p. So in this compact form for mu and sigma, we can use Python to solve this problem in a different way as has been done in the book. And then we can answer the question about the probability that is asking. So the probability that the number of flows per wire in this sample is less than 0.6. And for that we are going to use the central limit theorem. Okay, let's jump into Python. So we have our Python file. So this is the problem that we're solving. So we have two vectors, so we are going to have x and the random variable, discrete random variable, and p, which is the probability of the random variable. So let's start in our Python code. So initially I'm going to reset all the variables possible, and I'm going to import two libraries, NumPy and for the linear algebra part, and SciPy stats as st. So from this library I'm going to use the normal CDF function. So I'm going to define two arrays, one is x and the other one is p, and they are NumPy arrays. So this is the way that we define the arrays. And so let me execute this one. So we execute them, and then let's continue. Now the population properties, so we have that mu is equal to the dot product in between x and p vectors, and sigma, the variance, is the dot product in between x minus mu squared. So this square is for every single element in this vector, and dot product the probability, and then I'm printing the values. So let's execute. So we have the mean is equal to 0.66 and the variance equal to 0.5244, and this is for the population. Now let's jump into the sample. So the question is, what's the probability that x is less than 0.6 in our sample? So the sample size is 100, so it's large, it's greater than 30. So we can use the central limit theorem, in which x, the mean of the sample, is normally distributed with mean mu and variance sigma squared over n. So we're going to compute sigma, which is the standard deviation, as the square root of sigma squared over n. And then we are going to compute the CDF, so that's the integral from minus infinity to 0.6 of a normally distributed function whose mean is mu and variance is sigma. So this is the way that you have to tell Python, or this Python function, to compute the CDF, the cumulative density function. Okay, so if we execute, so we have that the probability is 0.20. So that's the probability of x being less than 0.6.